Okay, dear students, let us start from where we left in the previous lecture. And one of the consequences of Hahn-Banach theorem that I didn't do, let's do it now, is that, let me write it as a theorem, that all finite dimensional subspaces of a normal linear space are complemented, and which what I said in at the end of the previous lecture. What is a complemented subspace of a normal linear space? Now proof. Okay, now let X be a normal linear space and Y a finite dimensional subspace of X. It means that, let us say, dimension of Y is equal to n, which is less than infinity. That's what we mean by finite dimensional space. Now we can then choose a basis, a Hamel basis. We can choose Hamel basis, let me call it, of n vectors. I runs from 1 to n for this vector space Y. That means, now for any x, that means by definition of Hamel basis, for any x belonging to Y, there exists unique n scalars alpha I belonging to k. Of course, I lies between 1 and n, such that x can be written as summation alpha I xi I runs from 1 to n. Now this should be true for all x belonging to Y, because Y is a finite dimensional subspace. Now what I do next is that I define this G sub I to be a map from Y to K, which would map vectors inside Y to their scalar field. I define G sub I of X to be alpha I. By that I mean G1 of X is a functional that sends X to alpha 1, right? Because X is a combination of alpha, a linear combination of xi's in which alpha I is figure. So it sends it to the first scalar in its linear combination. Similarly, I have got another function that sends x to alpha 2. So these are basically n functions that send vectors to the field K. Now, G I is linear. It's a very simple exercise. And also I have, if you look at your notes, I have done there that it is indeed a linear map. Very straightforward, very simple. Furthermore, since Y is finite dimensional, every linear map on a finite dimensional space is automatically continuous. So Gi is linear, easy to show because Y is finite dimensional. That means Gi belongs to Y star for all I running between. So I've got now n functionals defined on this subspace. Now what should I do now? Of course, Hahn-Banach theorem. This Gi can be extended to a functional. Now this Gi can be extended to Fi belonging to X star. Well, I can define a functional Fi belonging to X star such that Fi, when restricted to Y, becomes Gi. Okay, so now Fi, what is Fi? Fi is now a map from X to K, and for every X I have got this map Fi, right? Which is linear, continuous, so on and so forth. And remember that Gi of X is equal to alpha I. And Fi, when restricted to Y, when we apply it on the subspace Y, its application is the same as that of Gi. And of course, these are n maps, right? Now what I do, I define P from X to Y, a map from X to this subspace, by P of X is equal to summation I runs from 1 to n Fi of X into xi. Now this is of course a scalar because fi is a map from x to k. Now put x here, we get to k. So this is a scalar inside k, and xi's are bases of y. So what does that mean? That means it's a linear combination of the bases of vectors inside y. Therefore, it is a vector inside y, right? And since each of fi's is linear and continuous, then p is linear and continuous. P is linear and continuous, right? Because a finite sum of linear maps is again a linear map, and a finite sum of continuous maps is again a continuous map, right? So it is linear, it is continuous, and P is onto. Okay, because for every x here, there would exist some combination of xi. So fi's run over all of k, right? Because fi is basically a linear map, so it has to run over all of k unless it is a zero vector. So it runs over all of k, so therefore this thing runs over all of y. So no vector in y is is not, unmatched by a vector in x. So that means it is an onto. So p is linear, continuous, onto, because fi is linear, and furthermore p is idempotent. So if I show that p is idempotent, so then I have found a linear continuous projection from x to y. That means y is a complemented subspace, right? So complemented. So I have to show that p is idempotent, and I'm done. Idempotent. Then it's done. So let's see now. P square of x is equal to p of x. What is p of x? P of x is summation I runs from 1 to n fi of x xi, isn't it? Okay, but then since p is linear, I can take these scalars out. So it is summation I runs from 1 to n fi x into p of xi, right? Okay, but what is p of xi? Now you have to remember how is p defined, right? For that you have to see how is fi defined. So p of xi, we know that p of x is equal to summation I runs from 1 to n fi of x xi, right? So that means p of xi, right? P of xi would be like, what would be like? So p of x is this. What would be p of xi? Now remember this. Okay, now look at p of xi. P of xi would be nothing but xi. How? Now look at this. P of x is defined like this, right? So how is fi of x defined? Because p of xi would be basically, let me write it a little detail. I runs from 1 to n fi of xi xi, right? And what is fi of xi? Now remember that xi's belong to fxi's belong to xi is a basis inside y. So that means it is the same thing as I runs from 1 to n gi of xi xi. Now how is gi defined? Gi of x is equal to alpha I, or should I write here gi of summation alpha I xi is equal to alpha I. That means gi of xi, which can be written as 0 into x1 plus 0 into x2 plus so on and so forth. At some stage you would have a 1 into xi plus 0 because 1 into xi is xi. So if you look at how this thing happens, it means that gi of xi should be, what do I have, should be just xi. No, it should be 1, sorry. So p of xi should be gi of xi should be equal to 1, right? And how about gi of xi minus 1, any other vector? Now if this thing matches, it would be 1. If I and I matches, it would be 1, otherwise it would be 0. So this would be gi's of xi's would be, when these i's match, it would be 1, otherwise it would be 0, so it is just xi. So this would be just summation I runs from 1 to n fix into xi, which is the same thing as p of x. I hope it's clear, but you do it yourself also and work it out. So that means it is idempotent that p square s is the same as px for all x. Therefore it's an idempotent map. So we have found a linear idempotent projection, and it's done. We have shown that every finite dimensional subspace of a normal linear space is complemented inside that normal linear space. So now, yes, I want to here give you an assignment for which I will mark you to find the dual of CAP. So find this. What is it isometrically isomorphic to? Like we showed the duals of other concrete spaces, if you do this, that would be an assignment. Okay, so that almost finishes our unit 1. Not it actually finishes our unit 1. So let me start with our unit 2nd of functional analysis. Now, okay, now let's start with where we left in the previous unit. That was dual. Now for every x a normal linear space, right, there exists its dual. Needless to say, it is basically outbounded linear operators from x to its field, right? Now this is true for every normal linear space, and of course this x star is the normal linear space under the subnorm, that is norm of f is equal to supremum norm x equal to 1 modulus of f of x, right? So it is itself a normal linear space. Then it must also have a dual, because every normal linear space we can define a dual, it has a dual, right? So since x star is also a normal linear space, I can think of x star a star, right? It is the dual of the dual, right? So what I have now is we denote it by x double star. By that I mean all bounded linear operators from x star to k, because x star is a normal linear, in fact it's a Banach space, right? So this must also be a Banach space. Of course its norm would be the same. What would be its norm? Okay, now if some capital F belongs to B x star k, right, then of course norm of f would be equal to supremum norm f equal to 1 mod of f, right, where of course f belongs to x star. So it is also a Banach space, because it is of course a dual. It's a dual of a dual. We call it bidual, right? Now what I do is I do something like this. Now this is one of the very interesting and important things in functional analysis. Now what I do is this. Now let f belong to x star. I define a map f from, now think about it, I define a map f from x star to, let me call it f sub x, just to, because it is the usual notation. But important thing is you just keep your attention to the definition. I define a map from x star to k by f of x of f is equal to f at x for all x belonging f belonging to x star. right? So since I am talking about fx, it means that x belongs to x. So this is a scalar because f is a map from x to k and x belongs to x, therefore fx belongs to k. So for each x, I can define a map f sub x, which is actually a map from x star to k. Right? Now, actually, I'm flipping things here. Now, firstly, I thought of x as something in the domain and f acting on it. I can also think of x acting upon f because f, there are lots of f's. I've got a well-defined set x star. So I can think of as if x is this expression as if x is fixed and f runs over all these x stars, so it becomes a map on x star for a fixed x, right? Furthermore, which is rather obvious, fx of f1 plus f2 is nothing but f1 plus f2 applied to x, and given our operations defined in x star, so this would be f1 of x plus f2 of x, which is f sub x of f1 plus f sub x of f2. So similarly for the scalar multiplication, so it is a linear map. It is indeed a linear map. Not only that, so I have defined now, so I've got x star, so I have defined f sub x for each x belonging to x. I have defined fx of f to be f of x. So then this f sub x is a map from x star to k that is linear. Very easy to prove. Furthermore, mod of f sub of f is the same thing as fx, but we know that this is less than equal to norm of f into norm of x. Write it as norm of x into norm of f. What do I have? I've got fx at f in mod is less than equal to norm of x. Let me put it in brackets. This is a fixed thing because I have fixed x into norm of f for all f belonging to x star. As per our definition, this is a bounded linear operator now, right? So it belongs, so f sub x then belongs, now this is a scalar valued bounded map that's also a linear map that's also continuous. This is precisely fx belongs to bounded linear maps from x star to k, which is the same thing as x star ka star that's equal to x double star. That means for each x belonging to x, I can find a f sub x belonging to x double star. Now, such that, now look at this. Furthermore, it tells me that norm of fx should be less than equal to norm of x. That's again important thing, right? So for everything x, there is something in x double star such that norm of f sub x is less than equal to norm of x. But also by Hahn-Banach theorem, we know that we did it in our earlier lecture. For every non-zero vector x belonging to x, there exists an f naught belonging to x star such that f naught at x at this non-zero vector is nothing but norm of x, and norm of f naught is equal to 1. So that means what I have now, that means if I apply my formula, it means that f sub x at f naught is equal to norm of x, and norm of f naught is equal to 1. Of course, this is, I can just put a mod around it because this is non-negative. Okay, so that means I know that, which means now for a vector of unit length, I've got norm of fx f naught is equal to norm of x, which means that supremum of these vectors, these fx evaluated at the vectors on of unit norm, that means norm of fx uska jo is set ka supremum hai, it should be bigger than equal to this member. And you combine these two, Now remember that is important. You get norm of fx is equal to norm of x. This is a very important thing. Okay, so the conclusion is that, let me write here. So conclusion is that for every x belonging to x, there exists something in the double dual fx belonging to x double star, such that defined by f of x at f is equal to f of x, right? Right? And norm of fx is equal to norm of x. Now keep this thing in mind. So that's what we have concluded. Okay, now let's move to the next thing. Okay, now next thing, let's continue with this idea. That is, in this way I can think of, now you remember that fx is now so I've got, suppose this is x. Now this is my x double star. For every x here, there exists something here. Furthermore, their norms are equal, right? So if I define now a map, now I can define a map from x to fx. I can define t of x. Let me, we usually denote it by psi of x is equal to f sub x. Then psi of x1 plus x2 is equal to f sub x1 plus x2. Now what is fx now? Now this is a function. Now this is a function. F sub x1 plus x2 belongs to x double star. So how do you know what a function looks like? We know it by its action on the vectors. And vectors are, so I have to look like this, f of x1 plus x2 at f. What would this be equal to? Of course f belongs to x star, because this means that it acts on x star with its codomain as the scalar field. Now by our formula this should be f of x1 plus x2, but f is linear, so it is f of x1 plus f of x2, now which is the same thing as f sub x1 at f plus f sub x2 at f, which is the same thing as f sub x1 plus f sub x2 evaluated at f. Now since this is true for all f belonging to x star, it implies that they are the same as functions, and f sub x1 x2 is the same thing as f sub x1 plus f sub x2, which would mean that I can write it as f sub x1 plus f sub x2, which is the same thing as psi of x1 plus psi of x2, right? Similarly, you can show that psi of alpha x is equal to alpha times psi of x. That means this map from x into x double star, this psi is linear, right? And of course psi of x in norm is equal to norm of course f sub x, but we have already shown that that's equal to norm of x. So it is an isometric isomorphism into x double star, because for every x there exists an fx here. We have not shown that for every fx there exists an x here. Then it would have been an isometric isomorphism onto thing, and they would have been the same spaces, which is not true. Now there exists fx's here which are not generated the same way by vectors inside x. So we call this psi the canonical mapping, canonical embedding of x into x double star. So psi of x is a subset because it into x double star. Now remember that. And furthermore, psi of x is isometrically isomorphic to x. Now remember this. X is isometrically isomorphic to psi of x, which is contained inside x double star. That means I can think of x as a subspace of x double star. Now remember, this is an important thing. Okay, so I can think of x as a subspace of x double star because it is isometrically isomorphic to psi of x using this canonical mapping. Then, and since it is isometrically it's a linear transformation, that is 1 1. Of course, everything that preserves the norm has to be a 1 1 map. You do that as a homework. That's straightforward rather, why as a homework. Okay, so there might be a situation in case psi is onto. In case psi is onto. That means in case psi of x is the same as x double star, then x can be identified with x double star because psi of x is identified with x. Means that x can be the same as x can be identified with x double star. If this happens, that is if psi is onto, this canonical map is onto, some authors use the letter j for it. Maybe I might have used j or psi. Look at in the note, but that's immaterial. Okay, then if this happens, we say if psi or j is onto this canonical map, or psi of x is the same as x double star, or x is equal to x double star, we say x is a reflexive space. Remember that when we talked about duals, I said that LP star is equal to LQ provided 1 by P plus 1 by Q is equal to 1, right? That would imply if I take P equal to 2, because P was greater than 1 less than infinity, it would imply that L2 star is equal to L2. That would also mean L2 star is equal to L2 star, which is the same as L2. So L2 double star can be identified with L2. So L2 is indeed reflexive, example of reflexive spaces. Okay, L2 double star is equal to L2. As I said, x is equal to, this is an example of an L2, a reflexive space. In fact, all spaces LPs are reflexive. Now LP star is equal to LQ, but that means LP double star is equal to LQ star, which is equal to LP, because again the same thing applies, provided 1 by P plus 1 by Q is equal to 1. So these are all reflexive spaces, provided that P is greater than 1. L1 is not reflexive because L1 star is equal to L infinity, but L infinity star is not equal to L1. So therefore, among the LPs, everything is reflexive except L1. Okay, so this was about reflexive spaces. Now let me summarize this canonical mapping. So canonical mapping is a map from x to x double star which sends psi of x to f sub x, where f sub x is a map, of course, from x star to k defined by f sub x at f is equal to f of x for all f belonging to x star. So this is our canonical mapping, and if it is onto, we say x is reflexive, and you can identify a space with its bidual. Now what you would see in our notes, now what is more comfortable, sometimes more puzzling actually, what we do, we denote all the vectors of x double star by small x double star. Everything here we denote by x double star, everything here we denote by x1 star, and everything inside x we denote by x. Well, that's a good notation actually. So if I use that notation, what would happen? So this would be x double star, this would be x star. So my canonical mapping would be from x to x double star, such that psi of x is equal to x double star, where x double star at x star is equal to x star evaluated at x for all x star belonging to x star. Now this would be writing the same thing in another notation. So you just keep that in mind. You can write this whole thing as this, and it would be used again and again in your यूनिट सेकंड एंड यूनिट थर्ड whatever जो भी आगे आप करोगे उसमें ये बहुत यूज होगा. And go through your notes, there are more details, yes, as I can see. So okay, then there is another concept. This was about reflexivity. There is another concept in what we call, that's basically a topological concept, what we call separability. Not those separation axioms. No, separability is something else that you might have done earlier. What is a separable space? We say a normal linear space is, let me call it X, is separable if it contains a countable dense set, a dense subset. That is, X is separable if there exists a countable set A contained in X such that the closure of A is equal to X. We call, for example, if I take R is indeed separable because Q closure, this means the set of real numbers, it's separable because Q closure is equal to R and rational numbers are countable, and its closure, if I take it along with its all limit points, then I would get the set of real numbers. That is the construction of the real numbers basically. So Q R is separable. In fact, LP is separable. The pth powers per sequences are separable for all p's less than infinity. All p's greater than equal to 1 but then less than infinity. This is a theorem. I think I should stop here. We're going to do it later.